2 sets, right?
2 sets, which would be how, so that would be
electrons, though.
pairs, right? So if it asks for pairs, it would be 2 pairs of unshared electrons.
That's for water.
That's for water. And 2 pairs of shared.
Unshared and unbonded are the same, right?
Unshared and unbonded, yes. And lone pair, they all mean the same thing. Alright, just a refresher on some other molecules and the difference between polar and nonpolar. If you take the electronegativity, remember this is where we had the electronegativity, so you'd write the electronegativity of chlorine, you'd write the electronegativity of carbon, and if it was greater than 0.5, it was a polar bond. So that's the first step, polar bond. Now, if they didn't cancel each other out, then that made a polar molecule. In the case of CCl4, they cancel each other out. So even though the bond is polar, the molecule is nonpolar because they cancel each other out. You guys remember that? Alright, this is polar because ammonia actually has a lone pair up here. So if you did the valence electrons or the Lewis dot, there'd actually be a lone pair up there. So there's more electrons on one side than the hydrogen. Over here, even though it's a similar shape to this nonpolar one, this has 1 chlorine and 3 hydrogens. Therefore, there's more electronegativity around the chlorine, so it's polar. And then this is nonpolar because they're canceling each other out. There's no area that's more electronegative than another. Questions? Alright, refresher on Lewis dot structures. So all of the alkali metals are going to have 1 dot. If asked you to do the Lewis structure, just 1 dot, because they have 1 valence electron. Question? Alright, all the alkali earth metals are going to have 2. Boron, so we're skipping over to the other side of the periodic table, we'll have 3. All the carbons have 4. Nitrogen, you start pairing them up again. Oxygen's going to have 2 free electrons. Fluorine's going to have 1. And the noble gases are full. Y'all remember that? Alright, Lewis structure. So to figure out the Lewis structure of a molecule, so those were just individual elements. Now if I said, give me the Lewis structure of NH4 or NH3, you'd count the total valence electrons. So let's do NH3. So how many valence electrons does nitrogen have? Valence electrons. 5. And then 3 hydrogens will give us 3. So we have a total of 8. So draw a provisional skeletal structure. Remember, we're going to do it with the one that can make the most bonds goes in the middle. Okay? And then everything else coming out from it. So I'll put nitrogen here, hydrogen, hydrogen, hydrogen. Alright. So now I count up how many I used. Each line is 2. So 2, 4, 6. So I've used 6. I have 2 left. Well, can I double bond a hydrogen?
No.
So what do I have to do? Yep, lone pair. So I distributed the remaining valence electrons. Check for octets. So hydrogen is good. It's sharing 2, sharing 2, sharing 2. Nitrogen has 1, 2, 3, 4, 5. Sorry, 2, 4, 6, 8. It's good. Life is good. Questions? Is it coming back to you? All right. On to thermochemistry. So you need to know the potential energy diagrams and all the terms. So you need to know where we find the reactants, where our activation energy is, where our activated complex will be, where our products are, and then our delta H. So for an exothermic reaction, this is what our potential energy diagram looks like. Our reactants start higher than our products end, and we're going to have a delta H that's negative. And over here, the reactants start lower than what the products end us. So this is going to give us a positive delta H. Any questions on this part? You need more time to write?
Yeah.
And I will also put this up on YouTube, assuming it comes out okay. Can I move on to the next thing? Alright, a little more about the endo-exothermic process. So we have to add energy to melt ice, so it's endothermic. We have to add energy to evaporate something, so it's endothermic. We remove energy when we're going from a vapor to liquid water. So it's giving off energy to the surroundings. And then same for liquid water to ice. So you'll need to know some examples of exothermic chemical reactions. If I asked you which was an exothermic chemical process, and I gave you the choices of evaporating water, photosynthesis, melting ice, or the combustion of gasoline, which would you tell me? Believe in your answer. Say it proudly. Combustion. It's exothermic.
Wait, so if you add energy,
Because it gives off.
it's gonna run.
If you have to put in energy, it's endothermic.
So freezing is exothermic?
Mhm. All right. Now we have our calculating delta H. So remember, delta H is the bond broken, or in other words, the reactants, minus the bonds formed, so if we have to add up the bonds, we're doing bond energies. Remember, that was the first thing we started with, where you draw out the Lewis structure, and you have to actually count how many of each kind of bond you have, and then calculate. So in this case, if I drew them out, if I drew out H2, I have two H2s. So that's an H2. I have two of them, and according to the table, which you guys will be given, each H to H bond is 432 kilojoules. So that would equal 864. We have one O to O double bond at 494 kilojoules. so that's still that. And then what it'll look like on your table is gonna be an O to H bond. So you would have 2 O to H bonds in each water, for a total of 4 O to H bonds. Does that make sense? So it's gonna be 4, an O to H bond would be 460, so you multiply that out. And then we take our delta H equals the bonds broken minus the bonds formed. So that's bonds broken and then bonds formed. That gives us negative 482. Is it endo or exothermic?
It's
It's exothermic. Negative delta H is exothermic. Alright, so that's our basic one where we're adding up each individual bond. Questions? Alright, now we have